The following video module covers the use of the Catapult Design Analyzer Design Advisor. Although high-level synthesis has been in production for almost 2 decades, designers still struggle when trying to optimize area or improve runtime. Bad coding style is typically the cause of long synthesis runtimes and larger area. Historically, it has been challenging for new users to high-level synthesis to identify and fix these types of issues. Usually, an expert is needed to help solve these kinds of problems. The Design Analyzer Advisor automatically identifies the worst coding issues. Let's begin by looking at a simple example that demonstrates how bad coding style can increase area and cause long runtimes. In this very simple example of roughly 70 lines of C code, the design does things such as packing an array into the lower elements, calculating leading ones, zeros, trailing ones, and trailing zeros, and does a conditional accumulate based on a bit pattern. Looking at the design constraints, all loops are fully unrolled and the main loop is pipelined with an II of 1. And notice then that the loop iterations are either 40 or 50 loop iterations, which is not an unusually large number of loop iterations for a design. After the design has been synthesized, looking at the table view, we can see that we have a latency of 20 cycles, which is a somewhat large number of C steps for the design schedule, or in other words, a deep pipeline. The area is over 200,000 square microns. And if we look at the runtime, we can see that this relatively simple example took almost 2,000 seconds to synthesize. So more than 30 minutes of runtime to build a very simple example. Lastly, if we look at the breakdown of area, we can see that this design is actually dominated by register area. More than half of the design is made up of registers, and this would make sense considering the pipeline depth is so big. So the questions that need answering are, why is the runtime so long? And can the area be improved? We can use Design Analyzer to answer these questions. After Design Analyzer has launched, we immediately notice some differences between this example and our previous simple example. In this example, both the RTL schematic and the design schedule view are not being rendered. And this is because there are many thousands of operations that would cause rendering to slow down Design Analyzer. This is the message we see displayed in both the RTL schematic and the schedule view. So we can see that the schematic contains over 19,000 items, and so rendering this may take a long time. However, if we wish to see it, we can click on the pane and the rendering will happen and we'll have to wait. Let's go ahead and look at the schematic just to see what was being created from our simple example. After a couple minutes, the schematic renders and we see what looks like a giant sea of gates. So it is not possible to determine how the structure of this RTL has been created from the C code. Prior to the creation of the Design Advisor, Design Analyzer still provided valuable information to allow users to pinpoint the areas of complexity in their design that were causing an explosion in runtime and area. This can be found by going to the Object view and selecting the Locations tab. What this shows us is essentially a heat map of the number of operations per line of C code, with the largest number of operations being listed at the top. So selecting this line of C code in the Locations tab shows us that there are several thousand operations that were created during the synthesis process of synthesizing the following loop in our design, which is essentially packing an array with a bunch of values based on some bit vector. Although the location information allows us to pinpoint areas of complexity, it does not provide us any information about how we would go about restructuring our C code in order to get a better result. This is why the Design Advisor was created, in order to provide that type of feedback to the user. The advisor is actually part of the default perspective view, but there also is a built-in perspective that we can use to look at the results from the advisor. And we will select that by going to the window menu, selecting perspectives, and selecting the advisor perspective. The Design Analyzer Advisor currently detects 3 of the most problematic coding style issues related to area and runtime. The advisor will list out any issues in the Issues dialog, which can be selected. The Design Advisor provides a description of the issue as well as an example of what the bad coding style might look like, and additionally provides a coding recommendation about how to restructure the code in order to get better runtime and area. Each issue is selectable, and the issue details are cross-probable to the source code, showing both the enclosing loop as well as the condition that was detected in the source code. The Design Advisor detects the following coding style issues. Conditional assignments. Having conditional assignments inside of partially or fully unrolled loops will often result in a dependency chain. The key with these types of coding style issues is to restructure the code and make it so that the assignments are unconditional. Dynamic write index. Writing to an array that is mapped to registers with a dynamic index inside of a loop that is partially or fully unrolled will cause an explosion in both runtime and area. And lastly, deeply nested conditions. This typically is a result of combining loop unrolling with a loop body that contains a conditional break. Unrolling loops with conditional breaks typically results in a priority encoded chain of logic that is both bad for area as well as runtime. The advisor lists out the different issues it finds for each one of the coding style scenarios it detects. Starting with conditional assignments, we can select the first issue, select the condition, and filter to see what we get. What is being shown here then is that the unrolled loop with a conditional accumulate has created a dependency chain of logic that is causing the schedule to be pushed out to almost 20 C steps. This will increase not only register area, but also will not help runtime. Scrolling down in the description of the problem, the recommendation from Design Advisor is to restructure the code so that the accumulate is written unconditionally. In other words, try to restructure the loop body so that all assignments are unconditional. Looking at the dynamic write index issue and cross-probing to the code, it can be seen that the index for writing the count array is being conditionally incremented based on a bit set in the holes array bit vector. Because this loop is fully unrolled, that means that the dynamic index count is being replicated 40 times, which again is going to result in larger area and worse runtime. The recommendation for proper coding style is to restructure the code so that the write index will become constant after loop unrolling. And lastly, looking at the deeply nested condition issues, it can be seen in the code that there are 4 different loops that are being used to compute things like leading ones, leading zeros, trailing ones, and trailing zeros. These loops have a conditional break based on whether or not a bit is set in the bit vector. And this conditional break is creating a priority encoded chain of logic, which we can see by filtering to the problem and looking at the schedule view. And what we see then is a giant dependency chain of logic that has been created where there is a selector for each loop iteration that either feeds the next selection or feeds to the output. Scrolling down and looking at the coding recommendation, what we see is that the code should be rewritten to remove the conditional break. For these types of problems, it often requires thinking about the kind of hardware you want to build and what it should look like. For example, doing a computation such as leading ones or leading zeros can be most efficiently implemented by creating a log2 based structure where there are log2 levels of logic compared to the n levels of logic by unrolling a loop with a conditional break. After rewriting the design with the recommendations from the Design Analyzer Advisor, the latency has been reduced from 20 cycles to 4 cycles, and the area has been reduced to about 100,000 square microns. Compare this to the original implementation of 170,000 square microns of register area, as well as a total area of 237,000 square microns. The reason for this large reduction in area is primarily due to reducing the amount of registers because the pipeline depth has been reduced from 20 cycles to 4 cycles. So looking at the detailed register scores, we can see that the register area is now about 50,000 square microns compared to 170,000 square microns with the original implementation. So we've reduced register area by a factor of 3. Additionally, looking at the runtime has gone from the original version of about 2,000 seconds to 876 seconds. So the runtime has been reduced by almost half, and the area has been reduced by more than half. This concludes the presentation on using the Design Advisor in the Catapult Design Analyzer.